So at the end of last class, we were working through a confidence interval question about the number of chocolate chips in a bag of Chips Ahoy cookies. And I ran out of time, and I ended at that top row where we had done some math and moved some things around. And then I got back to my office, and I'm like, I better finish this. And then I got going, and I'm like, wow, this is a little bit hard. But I saw it through to the end because math is easy. You just have to know what to do. The numbers aren't that hard. So I want to walk you through what I did up in my office so that I can show you that it worked. And then I'll show you about the super equation that was in the textbook that if I just would have looked at that, would have made it 10 times easier. All right. So we ended with top row, right? 2.55 divided by, and that's the standard deviation, 1 over square root of n. You think about, do the math, so that's a fraction. I have a number, 0.0224 equals 1 over the square root of n. Remember that trick from high school when you're multiplying fractions? Where if you put the two fractions equal to each other, you can multiply across diagonally. So this 1 in the numerator times this 1 in the denominator equals this 0.0224 in the numerator times the square root of n in the denominator. So I did that sort of cross multiplication. It gives you 1 equals this 0.224 times the square root of n. Again, turn it back into a fraction and divide by the thing that we're multiplying n by, and you get 44.6919 equals the square root of n. How the hell do you get rid of a square root? Yes, you don't do an inverse. I don't know why in my head I had inverse, so I'm Googling inversing square roots, and no, you just square the damn thing. So you take the square root of n squared, which means you square the other side, and if you square 44.6, it comes to 1,997.4. So if I want to construct a confidence interval 10 chips wide, I have to examine 1,198 bags of Chips Ahoy cookies. And at that point, you realize, wow, you're going to waste a lot of cookies doing that, right? And that's if you want a confidence interval that is really, really small. All of this was high school math. I had, just a little bit of a remembering of to do the trick here and to square this down here. And then I said, well, geez, did they really want me to do all that? And then I looked in the book and there's this equation. So I'm like, let's see if you got the right answer. I already know I got the right answer because I looked it up in the back of the book. But they say, all right, if you want an estimate of the number of cases to construct a confidence interval, and you know how exact you want to be, we can estimate that. This little mark next to the n, anybody know what you call that? It's a prime. N prime. I think it should have a little hat, but they went with prime in the textbook because you're estimating an n. You take the z-score of the confidence interval you're constructing. So we're constructing a 95% confidence interval. I don't need to look that up. That is what for a z-score? 1.96 times our standard deviation, which we're given, which is 114.01, because you can't forget the 0.01. Yeah, that has a little hat on it too. Whatever, don't worry about it. Again, you're always given what you need. And then it says take the width of the confidence interval that you want and divide it by half. Because remember, two sides. So really what we're looking for is 5 chips away. So you do the math, and then you square that. So you do the math, replace the 1.96 with the standard deviation, divided by the 10 chips wide, divided by 2 itself, which is 5. And you multiply across, and you get the exact same answer I just got by doing it the way that I thought I could do it. Bucket on the floor. Right? I didn't know of this equation, so I said, well, this is what I do know. I'll take the question, plug it into what I do know, got the answer. Now that I know this equation exists, you could just do this. This is easier. If I was given a homework problem, I would use this. There's less cursing involved with this. There's also less of an opportunity to screw up, right? Because look at that. I did that in like, this is plugging in, this is consolidating. I did that in like, what, 2-3 moves? This is slide 2. It took me 2 slides. I accidentally deleted the other one. All right, to do it this way. But I knew this way would work because I know how z-scores work. So I knew if I just sort of reverse engineered what I was looking for, I'd get it, and I did. So yay me. I took what I knew, applied it to the question, and found the answer. And I would have been more appreciative if I knew that there was another equation that I could have used that was a lot simpler. So, yeah. All right. So that's confidence intervals. We have a normal distribution. We take what is given to us, which is usually the idea of a mean or a sample mean. We take our critical value. We find the area in the middle, which is usually 1 minus our critical value. And then we work the z-table like we know it works, or the t-table if it's really small. Okay? That's what we do. We know z-scores. Okay. Today we're going to have a little bit of a wrinkle. Right? We know z-scores. Let's think about how we can take this framework and do more with it. So today I want to introduce you to the idea of using proportions. Now I'm going to give you a warning. I didn't see this in the textbook. But in political science, we use a lot of proportions for our dependent variables and our independent variables. We use a lot of dummy variables, categorical variables, ordinal variables. We don't always have situations where we're trying to count a number of something, right? The number of chips in a bag. That's a counting number. We don't have a lot of those in the social sciences. We can count income. Like, that's a nice continuous variable. How much money do you earn in a year? But when it comes to political science, we tend to think of even some of those counts as proportions. So when we talk about a race for the president, how do we think about who the vote total? How do we typically talk about it? All right, you're actually counting. But how do we talk about? So who's in the lead today? What do you mean it's tied?
I think Trump was like up by 1 percentage point.
Okay, so when we talk about political races, we always talk about it usually in terms of percentage points, right? So it's 44-43. That's not a count. That's a proportion. Okay. So a proportion, or why are you doing this? or a percentage is paying attention to numbers as part of a group. Let's say 44, 42, 3, and 1, right? If you got Clinton, Trump, Johnson, and Stein. Okay? We're talking about these as a percentage of votes for the candidate, of votes cast. So we're not going to say President Obama beat Mitt Romney by 5 million votes, because that doesn't give us as much information. Well, is that a lot or little? But when we say President Obama beat Mitt Romney by 5%, then we get a better idea of, okay, right? So sometimes the proportion helps us understand comparatively the difference between two candidates, sports teams with winning percentages. Okay. But what we've been discussing has always been a mean number, the number of chips. Your score on an exam in terms of the SAT or the ACT or the IQ, right? You get X amount of points. What we need to start doing is thinking of these numbers as proportions. So let's say we have a dummy variable. I need the bottom of the screen. We have a count, right? So I can count the number of males, 1,232. I can count the number of females, 1,600. But that number by itself does not give you the context of how frequent it is in the data set. But if I were to tell you the proportion of females in this data set is 56% or 0.56, that gives you some context for that number. The proportion of males is 44%. More Greek letters. That's pi. You recognize it before in its other meaning, the 3.1415926. Actually, I kind of made up some of those. Right? You remember that one. Because pi as a number is actually what? You know how they know it's 3.14? Why is pi a magic number? Well, it's magical that way, yes. But it's a constant because the size of a circle is always, all right, how do I do this? The area of a circle is a result of the proportion of the radius to the circumference or diameter, one or the other. Geometry is useless. All right. And it becomes a constant. Well, that's like a magical proportion. So circles are always proportional because of pi. So they use pi. Pi p, proportion. I don't know. All right. So we're going to start using pi's. Now typically with proportions, we use them most frequently when we have a dichotomous variable, where you only have two selections. But you can, by using subscripts, denote multiple groups. So what proportion of this sample is black? Yeah. So there's 400 total black respondents out of 2832. So that's like 1 in 7. So we're all okay with the idea of the concept of a proportion. Hope so. We can, with just a couple of tweaks, we can start using these proportions when we interact with our z-scores. And here's how we're going to do that. Because estimating, I can go back to this. When we use our z-scores, we usually are talking about the difference in the mean divided by the overall variability of our data. But the concept of variation, variability, standard deviations, standard errors, they don't work so well when you have data that is a proportion. So we have to compute these in a different way. So our new version of our standard deviation is going to be the square root of pi times 1 minus pi. Now let's think about this for a second, okay? Give me a pair of proportions that have little variation between two groups. Where there's a small amount of difference. Thank you. The square root of, let's pick one of them. Let's go with female. 0.5, was it 54? Yep, 6. Times 1 minus 0.56. Well, we already know that. 0.56 times 0.44. The answer is square root of 2464. Take the square root, not the square. Take the square root. Okay. So we do the math. How much variation is there? Well, according to this, it's 0.4964. Let's do an example where we have a lot of variation. Where are we going to see a lot of variation in this? Let's do white and black. Well, let's do white and non-white, because we've got that third category in there. So white is 2241 divided by 2832, which is the square root of the proportion of white people, 0.7913 times 1 minus 0.7913. I'm going to do this all at once because my calculator has parentheses. I got what's weird about that? So my standard error, standard deviation, whatever you want to call it, our measure of variation for whites and non-whites is 0.4, but for the male and females is 0.49. What's strange about that?
It's the same number of males and females, but it wasn't even close. Whites and non-whites.
What do you mean it wasn't even close?
Well, there were much more whites than non-whites. So they had bigger variance.
Right. So when we observed the difference, right, 79 and 21, you would think there's a bigger gap there, so the variance should be bigger, right? Whereas there was only, what is that, 56 and 44, it's a 12-point gap. The variance is actually bigger. So there's something about proportions that makes it counterintuitive. It just doesn't look right. Okay? So we have to be careful about that. Okay. This is an example of a question from the General Social Survey. Tell me whether or not you think it should be possible for a pregnant woman to obtain a legal abortion if the woman wants it for any reason. There's actually, I think, 4 or 5 different abortion questions in the General Social Survey. But this is probably the most, I guess you would say, the most extreme of the abortion questions. Should you be able to get an abortion if you want it for any reason whatsoever? The respondents answered, let's see, in this survey, 30,000 respondents. The answer was no 60% of the time, and yes 40% of the time. All right. So we have our values, and now we construct a, we have to compute the measure of variance around that. So I went with the yeses, right, 40.4. So 40.4 times 1 minus 40.4 with the square root of it gives me a standard deviation of 0.49. But I've got a lot of answers in this survey. I had 30,000 respondents, because what they did is they added up each year's survey. They asked the same question consistently for that many years. So to compute the standard error, oh, I'm sorry, this should be a pi. I don't know why it turned into a p. Let's go with that. All right, of my proportion, I take the standard deviation, divide it by the square root of the number, and I get a really small standard error. Again, why is my standard error really, really small? Large, not population, large sample, right? I had a really large sample. This is like 20 years worth of surveys respondents added all together. Now, if I were to construct a confidence interval around this, my proportion from my sample, oh, I know why I called it P, because it's a sample proportion. My sample proportion is 0.404. That's kind of like a mean, right? Actually, mathematically, it is the mean, because that's how many people responded as 1, and if all the no's are zeros, well, then they cancel out, and mathematically, a proportion is a mean. So I want to know the confidence interval at 95% around what I have observed in my sample. So I want my 95%. I use the same exact z-score process, even though it's a proportion. 1.96 times the standard error, plus or minus from what I've observed. So instead of it being my mean, instead of it being my x, now it's my pi or the p. Do the math, follow it through. So my 95% confidence interval says that the true proportion of Americans who believe that abortion should be granted at any time is somewhere between 39.4% and 41.4%. So what's the margin of error if we're talking in CNN TV terms here? One. Plus or minus like 1%, right? Because it's one on each side. That's that right there. Okay? So it would be really good if when we gave surveys and CNN is talking about if Clinton or Trump or Johnson or Jill Stein's in the lead, wouldn't it be great if they had 30,000 respondents? Yeah. So what does this tell us? If we were to make a comment about Americans' beliefs about abortion, what would you say? Right. A majority of people don't believe. You could even say a little bit more, right? Majority is kind of vague, right? Because majority is a whole range of numbers.
Say 60%, about 60% of people.
Yeah.
Don't believe.
About 60% of people do not believe that a woman should be able to have an abortion for any reason whatsoever. Okay. So we can take our sample and then infer to the population using our confidence intervals. Okay. Now, if I were to do that in this class, right, we did the thing with the keyboard. You all come up and you do it wrong, but you do it. And then I have to correct you. What do you think we would get? Looking at how we do this. We would get a bigger standard error because our n would be like 12. All right, it's actually 18, but still. No, I'm missing Zane. Or not Zane. John Tavia. Sit next to her. And the other Jake. So 17. I was going to put myself in there, 18. All right? So this number here would be a lot smaller, which means this number here would be a lot bigger. Bigger times 1.96, we'd have bigger confidence intervals. I'm not even going to guess where we're going to start at because you guys are really different than most Americans. You are more different than most Americans in your feelings towards Hillary Clinton. So I'm guessing you're a little bit more different than these guys, which is fine. But hopefully, again, remember, our proportion, just like our mean, hopefully will fall within 95% of population mean. Okay. So we can work with proportions just like we can work with means. Okay. So what's the next step? If we can work with proportions just like we can work with means, what should we start doing with proportions? What should we start looking for? No. Okay, you're just like randomly selecting words out of the sky. Peanut butter! What should we start doing? If now we know we can treat proportions just like means, what can we do with proportions? Twiddle our thumbs with them? Sell them on a street corner? Smoke them? What can we do with them? Let me rephrase this. Where did we leave off with when we were talking about means? What were we trying to do with them? We were just like, hey, this is a mean. I gotcha. We were tracking them down and caging them like animals. What were we trying to do with them? You want to play hangman? Okay, I really can't do this because my spelling's horrible. I'm pretty sure I miscounted that first word. Blankety blank with it. Or blanking with it. All right, guys. If the Cubs can win the World Series, you guys can do this. What is the whole point of this class? What are we trying to do? Shiny gold star for Joey, right? So, Hypothesis. Yeah, I was wrong. I told you. I was off. All right. For some reason, this doesn't like me. There we go. Okay. What is with you today, computer? Okay. So here's what we can start doing, right? So if we have a proportion of two groups, whether it's white, black, male, female, Democrat, Republican. If I want to get really screwy, I can add in those independents, even though they're fake. People with stars on their bellies, people without stars on their bellies, whatever. I can take two groups, and now I can start comparing them and see. So, given our abortion data, anybody want to venture a guess to explain why people don't think women should get abortion whenever they want? Yeah, literally for any reason, right? So if we think about how we frame the abortion debate, you can call this abortion as contraception, right? Which is they basically say it's a form of contraception. You don't want to be pregnant. It makes you not pregnant. Usually contraception works before conception, but this is the way, again, we can frame that debate this way. So why would some people say yes or no to this question? Because clearly what we are observing is a difference. People have different beliefs on this question. Where does that difference come from? Give me a variable name. Okay. What's your hypothesis?
I would say that specific religion or like this.
Give me a hypothesis.
I would say that Catholics don't approve of abortion at all.
Okay. So what should we do to test that hypothesis? Yeah, right? We need a number for Catholics and then the number for non-Catholics. And then we use the exact same framework that we had for z-scores. Remember when we did difference of means? You guys remember when we did that? A long time ago. We're going to do that again because I did things slightly out of order from the textbook, where we look at the difference between two groups minus the mu or the pi divided by a sigma thing to get a z-score. And then we're going to do hypothesis testing, and we're going to set a critical value. And we're going to see if that difference between Catholics and non-Catholics exists. And is the gap big enough to say that it's not part of the potential for random sampling error in our distribution? Now, hopefully, if we do this right, we'll have 30,000 people. Right? If they ask the survey year after year after year, we'll have a very small standard error. But we're going to find out.